Hello everyone, today I'm going to show you how to design the PCB for the PSOC 6 wireless module. This is an wireless module from Infineon Technologies. And for the design of this PCB for this particular wireless module, we are going to use the CY8C Proto 063 BLE as the reference. As the reference. So if you look at the PCB CY8C Proto 063 BLE, the wireless module is placed here, and these are the headers, pin extenders for the wireless SoC module. What you see here is the programming header for the wireless SoC module. And what you have on the left side of the PCB, this PCB section is the programmer, which is used to program the wireless SoC module. But in this particular tutorial, I'm going to show you how to design the PCB section for the wireless SoC module. We will not be bothered about the programmer part. The PCB will have a programming header which can be used to program the SoC, but the programmer will not be placed. So in effect, we are focusing only on the right section of the PCB of CY8C Proto 063. So where do we start? First, we need to install a PCB design software. I suggest KiCad. KiCad is an open source PCB design software. It is available for multiple operating systems, including Windows. Okay, so the first step is to download the KiCad software and install it. You can press the download button here, and then you can select the operating system as Windows, because I'm using Windows. And then you can select the GitHub location from where you need to download it. So the download has started. And once the download is completed, you can install the software. And once the software is installed, you can double click on the KiCad icon, which will be either available in the desktop or in the start menu button of the Windows operating system. The next step is to create a project in KiCad. So go to the file, go to new project, and select the folder where you want to create the project. In my case, I will select the desktop. You create the name of the file. Let me create it as a PCB PSOC 63 because it's a PSOC 63 BLE module for which we are creating the PCB4. So the project is named as PCB PSOC 63 BLE. You save the project. So once the project is created, you can see the project here. The name corresponds to the name that we have given. The new project has two files associated with it. One is a schematic file and the other one is a PCB file. If you want to know where exactly this project is created, it is created in the desktop. It is created in a folder in desktop. But if you want to directly go from the project here, you can right click on the project and then select Open Directory in File Explorer, which will take you to the location of the project. Yeah, so you can see that there are three files. One is the project file, a schematic file, and a PCB file. At any time, if you want to reopen the project, you can go to the desktop and then go to the folder where the new project is created. And then you can double click on the project file. It will open the KiCad. Alongside with it, you can see the schematic and the PCB file. Once the project is created, the next step is to create a custom schematic symbol library and a custom PCB footprint library. Many a times when you are creating a PCB, you might need to download the schematic symbol and the PCB footprint from website. Say, for instance, you might need to download it from DigiKey or from a vendor website like Infineon or NXP Semiconductors or TI. So if you want to house these schematic symbols and PCB footprints in your project, you need to have a custom schematic symbol library and a PCB footprint library. So let me show you how to do that, how to create a libraries, how to create custom libraries in your project. First, you go to the symbol editor. If you want to create a schematic symbol library, first you go to the symbol editor. Go to File, and then click on No Library. Select the project. So if you create a custom library with a setting project, the library will be included in your project folder. The advantage here is that when you copy the project and move it to a different laptop, or if you want to share this project with your friend, he'll be able to open the project, and he'll be able to use the library that is included in the project. However, if you are setting the new library as global, the library will be accessible. The library will be placed outside your project folder. It can be accessed by any new KiCad projects that you create in your system. But the problem is that if you copy the project and you paste it in your paste it in a different laptop or a different operating system, or if you want to share your project with uh, your friend will not be able to use the custom library. So in this particular tutorial, I want to show you how to create a project, how to create the custom schematic and PCB library with a setting project. So the libraries will be included in the project. So click OK, and this is the project folder. So you can see the project folder. And in the project folder, you're going to create a new library. Let us call this library as my library. Uh, this is a my library. The extension is KiCad underscore sim. So it's a library that houses schematic symbols. Now select save. Once you have saved it, it's a good practice to pin the library. The library is already pinned in this case, so you don't need to do anything special. So if it is unpinned, you can right click and pin the library so that it will be visible in the first row. So this is how you create a schematic symbol library. Let us now create a PCB library for the project. So close this and then open the footprint editor. So the footprint editor is loading. The footprint libraries that are available. It might take some time when you're loading the symbol editor and the footprint editor for the first time, it might take some time. So the footprint editor is loaded, and we want to create a new PCB footprint library. So go to File, Create New Library. Again, you select the project and click OK. And in the same folder where the project resides, you want the library to stay. So I call this library as My Library. The .pretty extension uh, indicate that it is a library that stores PCB footprints. Now click Save. Once library is saved, it has created the custom library. It is already pinned so that anytime you open the footprint editor, you will see the library in the top list. Now let us close the PCB footprint editor. Now let us open the schematic editor. Go to Preferences. Go to Manage Symbol Libraries. Go to the project specific libraries. You will see the library that you have added here. This is my library. This is a library which you can use to store the schematic symbols, custom schematic symbols, or the symbols that you download from the websites for the project, for you to use in the project. Now, if you want to see the PCB library. Let us close the schematic editor first. Let us close the schematic editor. Let us open the PCB library, PCB file, the KiCad PCB file. Go to Preferences, go to Manage Footprint Libraries, go to Project Specific Libraries. You see the library that you have added here. And the extension of this library is .pretty, which indicates that this is a library where you're going to store the footprints. Okay, so let us close this PCB editor and let us look at the project. So now the project has a schematic editor, a PCB editor. By default, when you create a new project, you see the schematic and the PCB editor. What we have done is we have created a library, my library, for storing the symbol files, and a my library for storing the footprints. You can see one more folder. This is a folder that is created by the KiCad, and this folder takes a backup of your project once in a while. So you don't need to worry much about this folder. It is taken care by the KiCad. So in the project, you see 4 files, which are the 4 files with which you are going to work on. One is a symbol file, the symbol library file, the PCB library file, the schematic editor, and the PCB editor. So the next step is to create the schematic for the PCB that you want to design. So in the KiCad project, double click on the schematic file. It opens the schematic editor. So here you have to add the components and then wire them together so that it looks very close to the schematic of our reference PCB, which is the Proto 63BLE PCB from Infineon Technologies. So let us first look at the schematic corresponding to this PCB. So scroll down this PDF towards the bottom. The PDF shows a schematic of the schematic. So let us look at yeah. So here you can see the schematic of the PCB section corresponding to the PSOC 63BLE module. So what we are going to do is we are going to add these components, add components that you see in this particular PDF page and to the schematic editor in KiCad. So the first component that we are going to add is the PSOC 63BLE module. So let us open the KiCad schematic editor. Then click on the icon corresponding to add symbol and search for the PSOC 63BLE module. So there is no module corresponding to the IC that has been described in the PDF. So let us go back to the PDF. So this corresponds to CY. The component name is CYBLE 41041604502. Let us copy this and check whether it is available in the KiCad schematic library. So the KiCad, once you download the KiCad and install, by default, it has certain schematic symbols, certain number of schematic symbols. Unfortunately, this particular module is not available with KiCad. So now the next step that you have to do is you have to figure out how to get the schematic symbol corresponding to this part. So let us open the browser, search for this part. Open the DigiKey. Typically, DigiKey provides the schematic symbol and the footprint for many of the components. So this is a module that you want the schematic symbol for. So let us go down. Yeah, you can see that the models are available. So the CAD models or the EDA/CAD models are available. So let us go to the model part. So the both the schematic symbol and the footprint is available. So what we can do is uh, you can download the symbol and the footprint. So click the select download and then select KiCad version 6 plus. The KiCad version that we have installed in our system is KiCad version 8. So anything above 6, the symbol and the footprint above 6 would work, and then click on download. So the download is completed. So once the download is completed, copy this download to the desktop. Now you unzip this folder. Let me go to the desktop again. So go inside. And you will see the schematic symbol. And within the footprint start pretty, you should be able to see the PCB footprint. Okay, so let us go back. Let us copy this path. Now let us go to the KiCad back. Let us close this. Let's just open the KiCad project. Let us open the symbol library, which we have created already. So select on My Library. Now right click and say New Import Symbol, because we already have a symbol which we have downloaded from DigiKey website. We are going to import the symbol. If you want to create a symbol from scratch, you can do that. And when you're doing that, you can use the new symbol option. But since we already have the symbol, use the import symbol. Go to import symbol, and then here you paste the path for the downloaded file, and this is a symbol that you have downloaded. Click open. Yeah, so you got the symbol, and the name of the symbol is CYBLE416045002, and it is placed inside the custom schematic library that we have created. So click on save. So that saves the schematic symbol. Now you close this window and go back to the schematic editor. And again, click on the add symbol option. Now, when you search for it, you'll find the schematic symbol under the option My Library. So you click on that and click OK. So you have placed the schematic symbol corresponding to the CYBLE 416045002, which is the part that is used in the PSOC, which is the part that is used in the reference board. Okay, so let us come back to the schematic again. Double click on the schematic symbol and let us look at the footprint. So yeah, so it is not associated with any footprint. So now the first thing that the next thing that you have to do is associate the footprint with the schematic symbol. And for that, we need to import the footprint that we have downloaded first. So we have already imported the schematic symbol of this component. We are ready to import the footprint of this component. So let us do one thing. Let us save the schematic and close the schematic editor window. Open the KiCad. About the KiCad project again. Go to the footprint editor. Go to the buy library, and here right click, and then there is an option to import the footprint. We already have the footprint which we have downloaded from DigiKey. So we'll go and import the footprint. So paste the path where the footprint is saved. Go to footprints.pretty and then select the footprint that we have downloaded from the DigiKey website. So the footprint is important. How you save the footprint to the My Library section. So how do you save it? When you try to close it, it will ask whether you want to save it or not. Click Save. So now it will be saved to the. Now you have to save this in the My Library section and click OK. Okay, so if you want to confirm whether that footprint is saved in the My Library section, open the footprint editor again. Go to the My Library section, and you can see the footprint corresponding to the CYBLE 416045002 part. Now let us close this window. Now let us go back to the schematic. Now double click on the module, associate the footprint. So click here, go to the My Library, select the footprint that you have just imported to the project. Now click OK. Now click OK here. So we have placed the schematic symbol in the schematic editor. We also associated the corresponding footprint with the schematic symbol. So the next step is to place the remaining components corresponding to the schematic, corresponding to the PCB. So what are the components that we need? We need some connectors for GPIO extension. We need a programming header, and we need the passives to be placed. And we also need a couple of switches. One is for resetting the device, and one is a user-defined switch, a couple of LEDs. So let us see how to do that. Let us see how to include these components. Let us add a few connectors first. Let us look at the PCB first. So you have this wireless SoC here, the BLE module. And if you want to program this BLE module, you need to have a programming header, which is a 5-pin header. And there are two headers on either side, one on the top and one on the bottom, which are GPIO extenders. So in total, we will have three headers for this PCB. So let us add three headers first. So go to the schematic, click on the add symbol section and search for connectors. So there are multiple different types of connectors. We will choose a generic connector with a 5-pin of 1x5. There is one row and 5 pins. So that's a 5-pin connector. Here we can select the footprint that we want. We will select the typical 2.5 mm vertical footprint. So this is a JST, this is a footprint for a JST connector. So click OK and then place this connector over here. So this connector will act as the programming header. We need two more connectors or the headers, which is for GPIO extension. So for GPIO extension, there are standard interfaces. One such interface is called the PMOD interface. And let us look at the PMOD interface. It is a 6-pin connector. So there are different types of PMOD interface. So we will select the GPIO type, which is a type 1 PMOD interface, and it has a 6-pin. It requires a 6-pin connector. So let us look at it. Let us add a 6-pin connector. We will add two 6-pin connectors, one for the top and bottom side of the PCB. So again, go to the connector, generic connector section, and let us select the connector 1.6. And we'll again use the JST footprint, 1.6 2.5 mm vertical footprint. So click OK. And you place two of them. So you select that, press Control C and then Control V. You get the two connectors here. Now the connectors are placed. Now the next thing that we need to do is to connect, wire them together. So for the PMOD interface, the 5th and the 6th pin are ground and VCC, and the rest are the GPIO pin. So let us label that first. So select the pins from the top to bottom, select the pins, and there's an option, right click, you get pin helper. Then there's an option for, let me see, wire. So by this option, you can have wires for all of these. And then you can again select these wires. Now what you can do is you can make the 6th pin as a ground. So right click here, add label, and make this as the VCC. So the 6th pin is a VCC and the 5th pin is ground. So right click here, add label and type ground. So you have a ground and VCC connected to it. So if you want to zoom in, you can use a scroll wheel of the mouse. If you want to drag it, you can right click on the mouse and drag it to left or right, top or bottom. Okay, so you repeat this procedure for the other connector. So the one option is that you can delete this and do a Control C, Control V, so that you don't need to repeat the process again. So let us, the next thing that we can do is we can have wires for these connectors. So these pins, you can extend the wires. One other option is you can directly label them. So this is an option to label these pins. Now here also you can label these pins. So click and select these pins by dragging towards the left bottom side. Now right click, you get pin helpers option. There is an option for net label. Okay. So the advantage of this method is that the grounds is that all the pins will get labeled, and this ground and this ground is auto connect. I mean, it's automatically connected. You don't need to manually connect them together. Now let us have some GPIO pins for these connectors. So let us say we take the last 4 pins and extend it to connect it to the header J2. So they are 6, 7, 5. So they are 5, 4, 6, 4, 7, 1, and 7, 2. So let us add here. So add label. So it will be P54. Then add label to the next wire. So that is P64. Then click on the next pin, add label option. It could be P71. Now click escape, then click on the next pin, right click, add label. You get a P7 of 2. So the first connector is done. Now we need to extend the GPS for the second connector. The one option is you can delete this connector, Control C, Control V, you get one more connector. Now you just need to change the GPIO names here. Let us make it P912, P91, 95, 96, and 92. So double click here. This is P91. This is P95. This is P96. And this, click on this label and change it to P9 of 2. So the two headers, the extension, the connection to the BLE module is done. The next thing is we need to have the programming header connected. So let us go back to the schematic of this reference PCB and look at the programming header. The pin number 1 is connected to the supply. Then we have ground, then we have reset, SWD clock, and SWD IO, which are the programming lines. Let us look at where the SWD clock and SWD IO lines are going to this PLE. So let us first have VDD enter ground. So select the pins, go to pin helper, and then you can say net label. That is one option. Now pin 1 is VDD. So double click on pin underscore 1 and say VDD. Then we have ground. Double click here and say ground. Then we have pin 3, which is reset. So let us look where the reset is going. Reset is XRAs. It goes to pin 42 of the BLE module. So the pin 42 of the BLE module is labeled as XRAs. So we can label this as XRAs. So the connection goes directly to the XRAs module. Then we have two more pins that goes to SWD clock and SWD IO. So if you look at here, the SWD clock is going to P67, SWD IO is going to P6 of 6. So the fourth pin is going to 67. The fourth pin is going to P67. The next pin is going to P6 of 6. So that is P6 of 6. So that is done. If you want, you can rotate it, or you can do a mirror image. So what we have here is we have the two headers for GPO expansion, and we have the programming header which is ready. So that is done. Now we have the BLE module here. What else we need? We need a button for resetting the BLE module, and we need maybe an LED which can be used by the BLE module. So if you want to toggle the LED, you can do that. And we need some capacitors on the supply pins. So we need a capacitor on the supply pins, which is a decoupling capacitor. And we need crystals. So we need two crystals. One is a low frequency crystal, 32.768 kilohertz, and one is the 24 megahertz crystals. So these are the components that we need to add. And there is also a user button that has been placed. So it is good to add a user button. So we need to have two user buttons, maybe a couple of LEDs, resistors which are passives, and two crystals. So let us start by adding the LEDs. So let us say that we need to have two LEDs. So go and click on the add symbol option. and search for LED. So you can select the LED and then you can decide on the footprint. So I decide to use a 0603 footprint. So 0603 footprint is selected. Click OK. Now we need two such LEDs. So let us Control C, Control V, copy and paste it. So you get two LEDs. Now let us look back the schematic. So the LED section is over here. One end of the LEDs are connected to the supply and the other ends are connected to two IOs of the CYBLE module, or the wireless SoC module through series resistance. So two series resistance are required. So let us look into that first. Let us try to add the resistors first. So search for the resistors. Let us search for the resistor. Yeah, so this is the resistor. For resistor also we can select 0603 as the footprint. Now click OK. So if you want to rotate a component, you can press the key R. And we need two such resistors. So you can select the resistor, copy it, and paste it. And now we need to have a supply, which is VDD. One option is you can place a supply port. So here we have the supply port. There is no footprint required for this. So you place a VDD over here and then wire them up. So you connect the VDD to one end of the LEDs, and the other end of the LED you connect to the resistor. And the other end of the LEDs has to be connected to IO pins. Let us take two IO pins. For timing, we'll take 04 and 51 as IO pins. 04 and 51. So let us rename this and label it as LED 1. Label this as LED 2. Now right click on this, pin helps, net label. So we'll have a wire first and then we'll label it later. So okay, now click on the wire and then say add label LED 1. Now click on the next wire and label that wire as LED 2. So what it does is it connects LED 1 to P04 and the LED 2 is connected to P5 of 1. So that's done. The placement of LED is done. The next part is to place the switches. So let us look at how the switches are connected. We need a switch for the reset, pin, and it is also good to have a switch, a user-defined switch. Okay, so let us first add a switch. So let us search for a switch And there are different types of switch. And one of the switch that that is commonly used is a single pole, single throw switch. So we are going to use a single pole, single throw switch. The footprints are not visible here. We will add it later. So add the uh, symbol for the single pole, single throw switch. And from here, you can add the footprint. So we'll add the footprint correspond to a tactile switch. So it is something it looked like this. So here you can see that it's a 4-pin switch. The pin 1s are shorted and pin 2s are shorted. So basically it's a 2-terminal device. If you short them, it acts as a 2-terminal device. So let us associate this particular footprint with this switch. So the footprint is assigned. Now, what we can do is we can duplicate this, press Ctrl C and Ctrl V, it duplicates. So one switch can be used for the XRES, and the other switch can be used for the connecting to a GPIO, which is a user switch. So let us look at back how the XRES switch is connected. So one end of the switch is connected to XRES and the other end is connected to the ground. So let us draw a wire. And the other end is connected to a ground. So either you can label it as a ground, or for a schematic, there should be always a ground terminal attached. So we will attach this ground terminal. Ground terminal doesn't need to have any footprint. Label this wire as XRES. Add label XRES. So that is done. So that part is done. For the second search, if you look at the second search, the user button, one end of the switch is connected to P04. So the way it can be interfaced is one end you can connect it to one of the IO pins, and the other end can be connected to ground. You don't need any resistors. So let us first connect a wire. And then label it. Right click and add label. Let us call this as switch SW. Let us label it as switch. And the other end is connected to the ground. So we can Control C, Control V, the ground, and connect it like that. So this is switch SW2. Let us call this SW2. And we need to assign SW2 to a pin. For time being, let us assign it to P50. So this would be SW2. Now click OK. Now it is a good idea to label them as GP0, GP1, GP2, GP3 so that you can also label the pins associated with GP0, GP1, GP2. Let us say, let us start with the programming header. For the programming header, the fifth pin is SWDIO and the fourth pin is SWD clock. So the P6 of 6 is SWDIO. So let us label this as SWDIO, and the P6 of 7 is SWD clock. So label this as SWD clock. Now we have to make that changes here as well. So this one is SWDIO. This one is SWD clock. So the advantage of doing this is we know which are the pins in the wireless SoC module which are utilized here. So let us change the naming convention for the pins associated with the connectors also, connectors J2 and J3 also. So let us label it P5 of 4. We will call it as GPIO 0, or we can call it as, okay, let it call it as GPIO 0. Maybe we'll just make it as GPIO 0. GPIO 0, GPIO 1, GPIO 2, GPIO 3. Now let us change the labels here as well. So this is GPIO 0. Double click and change the name. GPIO 1, GPIO 2, GPIO 3. Now we need to change the label's name for the pins associated with connector J3 as well. So this is 91, this is 91, 95, 96, and 92. So let us label it as GPIO 4, this one as GPIO 5, this one as GPIO 6, and this one as GPIO 7. Now let us rename this. So this would be GPIO 4. This would be GPIO 5, GPIO 6, and GPIO 7. So we are done with relabeling. Maybe we can take the mirror image of this connector so that all the connectors look similar. The orientation of all the connectors looks similar. Okay, so the next step is to have capacitor. One capacitor is needed on the pin VDD of the SOC module. This capacitor acts as the decoupling capacitor. So let us add that capacitor first. So go to the add symbol option, search for capacitor, and again for the capacitor also you select the 0603 footprint, then click OK. So the capacitor is available. So the capacitor, we can connect it somewhere here. And one under the capacitor has the VDD. So let us Control C, Control V here. So this VDD is connected over here to the pin 4 of the SOC module. And the ground is connected over here. Fine. So we also need to have an association of ground with the ground of the SOC module. Even if you don't do that, it is fine because the label is the same. So the ground here is connected to the ground of this particular terminal. And the next thing that we need to do is add the crystals. So we need to add 2 crystals and passives associated with the 2 crystals. So let us add the crystals now. So let us go to the schematic file and check. The first crystal that we want to add is a 32.768 kilohertz crystal. It has 2 terminals, and let us try to add that. So go to the schematic, click on the add symbol option, and search for the crystal. So we have a 2-pin crystal. There are multiple crystal options available. We'll select the 2-pin crystal. There are different footprint options, and you need to figure out the right footprint. So for time being, let us place the crystal and then look at the schematic. The crystal that we want is a 32.768 kilohertz crystal, and the part number is mentioned here. Copy this and let us try to search for this part number. So this is a part number, And when you look into the DigiKey, you can look at the package. It's a 2-pin crystal with it's a surface mount type, and the dimensions are 3.2 mm cross 1.5 mm. So you can double click here on the crystal, and we have to associate a footprint associated with it. So let us look at the footprint. Uh, so search for crystal, and select the surface mount 3.2 mm cross 1.5 mm dimension. So I think this should do. This is a 3.2 mm cross 1.5 mm crystal. Yeah, so this is also a surface mount crystal. So let us try with this. Let us for time being select this particular footprint. Then click OK. So the crystal is placed. Along with the crystal, you need to place along with the crystals, you need to place a capacitor. So there are two capacitors that need to be placed, and the other end of the terminal, one end of the capacitor terminal, one end of the capacitor is connected to the crystal, and the other end connected to the ground. So let us now place the two capacitors. So one option is you already have a capacitor placed here. Control C, Control V. Rotate it by pressing the key R. Uh, rotate the crystal. You need one more of this capacitor. Control C, Control V. And the other side has to be connected to the ground. So the ground will be on the other side. Now you wire them. Yeah, so wire them together. Now let us also give the values to these capacitors. These are 22 picofarad capacitors. So double click on them, and the value you write it as 22 picofarad. And value of the second capacitor is also 22 picofarad. Okay, so similarly, you can also assign the values for the resistors. For the LED, the series resistance, we will set it as 470 ohm. So let us set it as let us set the value as 470 ohms. Okay, let us set it as 470. Let us skip the units. Uh, oh, we'll have the units. Okay, so we have fixed that the value of the decoupling capacitor is 10 microfarad. So let us keep that as 10 microfarad. Okay, so let us follow the same convention. There's no space between the value and the unit. So 470 ohm. Okay, so that's done. Now we have to place the next crystal. So the next crystal is a 4-pin crystal with the pin number 2 and pin number 4 connected to the ground. It's a 24 megahertz crystal. So let us go and place that first. Yeah, so we have a crystal selected. So we want a 4-pin crystal, and the ground is on pin number 2 and 4. So this is a crystal. Now we need to have a footprint for that. So first let us search this crystal, copy, and go to the top. Yeah, so this is a crystal. Let us look at the let us look at the crystal once again. CKM. Yeah, so this is the crystal. Let us look at the package of this crystal. It's a 2 cross 1.6 mm is the uh, package. So let us look for 2 cross 1.6 mm. So this looks the package. This looks like the package. So we'll select the footprint 2 cross 1.6 mm for this and click OK. And you can place the crystal over here. Now let us also add the passives for the crystal. So we need 2 capacitors. We'll copy it from here. So one capacitor is connected to pin number 1. The other capacitor is connected to pin number 3. So let us wire it up first. This is connected to pin number. This is connected to pin number 3. Now you connect the ground terminal. Now you connect to pin number 2, and 4 is also connected to ground. 2 is connected to ground. So you need to place a ground terminal at the side of the 2 also. That is done. Now we have connections going to P12 of 7 and P12 of 6. Okay, so what to do? So let us take the 2 wires and label these 2 wires. So for time being, I will label it as X1 and X2. X1 and X2. Okay, so we have labeled these 2 terminals as X1 and X2. So X1 is getting connected to P12 of 7 and X2 is connected to P12 of 6. So X1 is connected to P12 of 7. So let us look at P12 of 7. So this is a P12 of 7. So replace this as X1 and P12 of 6 as X2. So the connection is made. Okay, so that completes the connection. Now the capacitor values are 10 picofarad. So let us change the capacitor values. Double click on the capacitor, change this to 10 picofarad. And this one also you change it to 10 picofarad. Okay, so that completes the addition of the crystals. So now let us look at the schematic if there is any other connections to be made. So we have the wireless SoC module placed, the extension headers are placed for the GPIOs. We have the programming header placed. We have LEDs which are connected to the IO pins of the SoC module. We have the decoupling capacitor. The crystals are connected. The 32.768 low frequency crystal. Let us label it. So this is 32.768 kilohertz crystal. So let us call it 32.768 kilohertz crystal. And this is the 24 megahertz crystal. So double click. This is 24 megahertz crystal. So you can keep it closer to the symbol. This is the 24 megahertz crystal. And yeah, so most of the components are already placed. Now let us see if there is any other connection that need to be made. There is a VPAC pin which is connected to the VDD through a 0-ohm resistance. So basically it is a short. So let us go here. So VPAC need not be the here. It is connected to the VDD. So VPAC is connected to VDD. So let us do one thing. So let us have a net label here and change the net label to VDD because it's basically connected to the VDD. There are pins which are not used anywhere. So P05 is not used anymore. P000 to P94 is not used anywhere. P90 is also not used anywhere. So delete those pins. P52, P53, P55 is not used anymore. Till here is not used anymore. Okay. So those pins which are not used anywhere in the schematic, we need to place a NOC connection over there. So place it as NOC connect. Now you select these pins, right click, pin helpers NOC connect. And similarly, the P90 has to be NOC connect. And this side, select these pins, put a pin, select NOC connect. And these three pins also need to be made NOC connect. NOC connect. NOC connect. Pin help NOC connect. And that completes our schematic. That completes our schematic. It's a good idea to name the schematic. So if you want to name the schematic, you can have it. We can say this is the schematic for the CYBLE 4160450 chip. CYBLE 41605 6045002. Yeah. So if you want, you can also give the name of the person who has designed the schematic and the date. But for time being, we will just place this text. Yeah. So that completes our schematic. Just save the schematic. That completes our schematic part. So once the schematic is completed, the next step is to check the schematic. KiCad provides a tool called the electrical rules checker in order to check the schematic. So click on the electrical rules checker tool and run the ERC. ERC stands for electrical rule checking. So run it, and if there are any errors with the schematic, it will display the errors. So the first error says that the label VREF is not connected anywhere. Let us look at the label VREF. So that is true. So it says that the label VREF is not connected anywhere. So let us look at the reference schematic. So in the reference schematic, there is a VREF which is taken to the extension header, which means that if you want to apply a reference voltage, you can apply, and if you don't want to, you don't need to have that pin. You don't need to assign anything on that pin, or you need not connect anything on that pin. So what we are going to do is we are going to uh, delete all markers. So whenever there is an ERC identified, there will be a marker that will be generated. And we are going to delete the VREF. And on the VREF pin, we are going to mention that there is it's a not connect pin. Now let us save this and run the ERC again. It shows some more errors, and uh, these are some of the errors which you can neglect. So one of the errors says that the a, a pin which is defined as a power output is connected to a pin which is defined as a power output. Is connected to a different pin which is defined as a power output. So in order to solve this problem of listing these errors, we can set it to ignore these issues. So you can go to the ignore test, then edit the ignore test option, and here go down, and we don't want pin conflict problems to be declared as an error. So we just ignore it, select OK, and now go to the violations tab, delete all markers, and run the ERC again. So this lists one more error, which says that the input power pin is not driven by an output power pin. And this is also not a problem. So in many cases, this is not a problem. So if you want to ignore this issue, go to ignore test, edit ignore test, and let us look at the issue. The issue says that input power pin is not driven by any output power pin, which is the uh, issue present here. Input power pin not driven by any output power pins. We want to ignore this issue. And click OK. Delete all the markers and then run ERC. Yeah, so there is no issue with the schematic. So the issues that we have ignored are those issues which doesn't create any problem. And any other issue, you should not ignore it, you should fix it. So right now there is one warning. Let us look at the warning as well. The warning says that both LED1 are attached to the same item. So you can ignore this warning. Uh, this is a this is an issue of labeling, but this is not something that is critical. So we can just ignore it. So there are 0 errors, and it indicates that your schematic is completed. You can save the schematic, and the next step is to uh, start the layout part for the schematic. So the schematic is completed. The schematic is error checked. There is no error associated with the schematic now. You are good to go with the layout part of the PCB design. So once the schematic is done, the next step is to create the layout. So we have done the schematic check and there is 0 errors. So let us close the schematic editor and then open the PCB editor. So you close it and then go to the project file structure, and you can open the PCB editor from here. So double click on the PCB file and it will open up the PCB editor. Yeah, so this is how the KiCad PCB editor looks like. Yeah, so this is how the KiCad PCB editor look like. One of the first things that you should do once you launch the PCB editor is to define the PCB stack. So go to board setup, click on the board setup icon, and in the board setup icon, go to the board stackup. So the in the board stackup, go to the physical stackup option. So here, the stackup is defined for a 2-layer printed circuit board. Typically, for many designs, people prefer 2-layer printed circuit board. But in case you need a 4-layer or a higher layer PCB designs, you have to manually adjust this. Here, there are only 2 copper layers. You have a central dielectric layer and upper copper layer, or the front side copper layer, bottom side copper layer. This forms the 2 layers of the PCB, 2 copper layers of the PCB. And on the top side, you have the mask layer, the paste layer, and silk screen. And similarly, at the bottom also, you have the mask, paste, and the silk screen layer. So ensure that the stack up is proper. In many cases, you can set these to the default values of the KiCad, provided you are going to design a 2-layer PCB. The next step is to fix the constraints of the design. Now, typically, these constraints are gathered from the PCB fabricator's website. Say, for instance, if you are going with a PCB fabricator like PCB Power, the PCB Power, the company will list out its technical capabilities and the PCB constraints, and you can use this information to populate the KiCad setting, the design constraints. Uh, so, if you are not sure about what constraints to fill in, you can copy paste the contents that is shown here, and or you can also go to the PCB fabricator website, get these details and populate it here, or you can send a mail to the PCB fabricator and get the details from them so that you can fill it in the KiCad board setup constraints window. Now, once that is done, click OK. So the board is set up, the constraints are given. The next step is you have to import the components, import the footprints of the components from the schematic editor to the PCB editor. So how do you do that? Go to Tools. There is an option for Update PCB from Schematic. Click on that. And they're taking some time. Yeah, so click on Update PCB and then close. So what it does is it imports a footprint of all the components uh, from the schematic page. The next step is to create the outline for your PCB board. And if you want to create an outline for the PCB board, you have to select the edge cuts option. This is the edge cuts layer. And then you draw a rectangle. So once a rectangle is drawn, you can then double click on the rectangle and adjust the height and the width. So let us keep the height as 30 mm and the width as say, let us keep the height as 40 mm and the width as say 75 mm. So you can define the height and width accordingly. So depending upon what is the length and width of the PCB that you want, you can adjust the height and width accordingly. The next step is to place these footprints properly. So if you want to place the footprints properly, let us look at the reference design we have been following. So let us look at the CY proto board and let us see how the other connectors are being placed. Yeah, so let us look at here. So we have a programming connector, which is uh, the 5-pin connector. The pin number 1 is over here and the pin number 5 is on the top. So let us first fix the programming connector. The pin number, so you can use R to rotate. And the pin number 1 is on the bottom side. And the pin number 5 is on the top side. So J1 is a silk screen. So let us keep it at the side so that it is a part of the PCB. And let us keep it at the edge of the board. Let us keep it at the edge of the board. Okay, so that is done. The next step is place these connectors. So if you look at here, the pin number 1 is over here and pin number 1 starts from here for the connector. So let us also use the same method. Click on the connector and press R so that the pin number 1 is over here. And the silk screen for that is kept on the side. Okay, now we need one more connector. So pin number of that connector has to be placed over here. So this is how the placement look like. So the connectors are placed. Now the next step is, so the connectors are placed. If you want, we can keep it a little bit. Okay. So once the connectors are placed, the next step is to place the remaining components. Let us place the BLE component here and BLE component somewhere here. Let us place the switches at either end. So you place one switch over here, the other switch you place it over here, and then you have these LEDs. So let us place the LEDs somewhere here. Okay, so let us provide some gap for the LEDs and keep it at the center. Okay, so the main components are arranged. Now you have to place the remaining components. So let us first fix the crystals. So let us first fix the crystal. So let us go back to the schematic to see how the crystal is arranged. You have a low frequency crystal, 33.768 kilohertz crystal, which requires two capacitors, C2 and C3. Yeah, so the crystal need to be connected to the wireless SoC module, which we have not done it. Let us uh, go back and do it. Look at the schematic. So if you look at here, and the low frequency crystal has to be connected to P01 and P00. So let us connect it. So that was not connected earlier. Let us label these wires. This is Y1 and this as Y2. This as Y2. So once the connection is done, you have to make these connections map to uh, P01 and P00. So P01 is going to be, it's not no connection, it is Y1. So delete it and P00 also you have deleted. P01 is going to be Y1 and P00 is going to be Y2. So right click on it, pin help us net label. You can change it to Y1 and here you can click on it. Go to pin helpers and say net label and now make it Y2. So you have modified the schematic. So once the schematic is modified, you have to run the schematic check again. And let us see if there are any issues. Yeah, so this is okay. This is a warning. There is no errors. So let us close here. Go back to the PCB editor. You can click this icon if you want to go to the PCB editor back. But since you have made the changes in the schematic, you have to import these updates from the schematic again. So update the PCB and say close. Now what we are going to do is we are going to fix the connections for the low frequency crystal. So the low frequency crystal is Y1 is a crystal name and C2 and C3. So let us figure out Y1 and C2 and C3. So we got Y1 and then we have C2 and C3. So if you look at here, the Y1 and Y2 are connected something like this or rotated. So the rotation has to be done such that the wire connection to these pins are the shortest. Okay, now take it here. So this is connected to Y1 and this is connected to Y2. So let it go here. Let this come here with a rotation so that Y1 you can straightforward connect it. Here you have to do a rotation and yeah, this is fine. Now the cell screen, we'll keep it here. The C2 cell screen also will keep it here. Okay. Now we'll do the connection. So we take a wire. This is for routing the track. From Y2, we connect it to the Y2 over here. Y1, we connect it here. From Y2, we connect it to the Y2 of the wireless SoC module. Y1, the connection is done. Ground connection is done. Ground connection is done. So this completes the connection of the low frequency crystal. Uh, the next step is to uh, place the high frequency crystal here. So go to the placement of the high frequency crystal and you have to look at where X1 and X2 is. So keep it closer to X1 and X2. Uh, yeah, so we have kept the crystal close to X1 and X2. Now we need two capacitors for this, which is C4 and the C5. So we have to figure out where is C4 and the C5 capacitors. So C4 is connected to the ground, and this one is connected to X2. So let us keep it like this, and the cell screen you keep it adjacent to it. Okay, now you make the connections. So take the track X2 to X2, ground to ground, ground to this ground, X1 here. The ground is connected here, and X2 is connected this direction. So the problem is you have to connect X1. So how do you connect it? An option is you delete this ground wire and let us connect the X1 first. X1 is connected. The ground needs to be connected. So what you can do is here you can place a wire. So how do you place a wire? Right click it and say place through hole wire. So let me delete this, go to the track and say place through wire. I think there is not enough space for keeping the wire. So let us do one thing. Let us create space for it first. Okay, so once it is done, take the track and right click and say place through wire. You place a wire here. Now you change the track to bottom copper side and take the route, and then you can take it this way. And here you have to again take it back. You have to have a place through wire here and then connect it to the ground. So this completes our design. So there is some artifacts over here that you can remove it. Okay, so the second crystal is also done. The next part is the decoupling capacitor. So you have to look at the decoupling capacitor. Decoupling capacitor is C1. So let us look at the decoupling capacitor. Take the decoupling capacitor, and the decoupling capacitor has to be kept very close to the ground. So Let us keep it here. Yeah, so let us keep it here and complete the connection. So the VDD will go here, and these two VDDs are connected together. The ground is connected here. So the ground connection is also done. Okay, so once that is done, the next step is to place the uh, switches. So we have an XRES connected to the switch, and we have SWT connected to the switch. So we have two switches here and two grounds. So let us complete the track for the ground. Now XRES is somewhere here. So from here, you have to take it and connect it over here. Connect these two XRES together, and the ground you connect it over here. So that completes the switch connection. And for this particular case, we have the SW2. So the way you can take SW2 is you complete the SWT connection, the ground connection. You can connect it over here. So that completes the ground connection for the switch. The next step is you need to have the LEDs connected. Now the LEDs have two resistance, 470 ohm resistance, R1 and R2. And after that, they need to be connected to LED1 and LED2. So let us look at R1, R2, take them here. So you have this R2. Yeah, so you have this R2 connected, and you have this R1 placed. So once it is done, you can complete the routing. So this goes here. The VDD is connected here. This connection is done. Now we have a VDD connection here. Yeah, so this is connected, and pin number 41 is connected to net 1. So let us look at the schematic. LED1 is connected to pin number 41. So here it is not labeled LED1. So let us fix that issue because there was a warning which was causing this problem. So let us delete this. Let us delete this, and right click here, pin helper, net label. Right click, pin helpers, net label. To have the wire connected first. The wire is connected, and right click here, add label, LED1. So that is done. Now go to save. Now run the ERC check. Yeah, still it has a label 1. So it could be one possibility is it could be because of this. Right click here, pin helpers, net label, and set it to LED1. Yeah, so yeah, still this issue is there. Let us leave this issue. This is not a big problem. Ideally, we'll have to remove this resistor and label it again. It will fix the problem. But let us go back. Let us update PCB from schematic. There won't be any change to the PCB because we have not made really any change. Now close it. So this is connected to pin number 41. So how do you make that connection? Go take it here, and here you have to place a wire. Now, once a wire is placed, you can take it through the bottom side. And there should be a wire again. Right click, place through wire. Now we have to go to the copper first, and in the copper, top copper, you complete the routing. So that is done. The next step is you need to connect the VDD together. So VDD is connected somewhere here. So how do you take that? Go to the, yeah, so till here it is fine. After that, we have to have a wire here, and then take it through the, complete the routing through the bottom track. Here you need to have a wire, place a wire. Now you take it the, complete the track through the top layer and connect it to the VDD. So the connections are done. Mostly the connections are done. Now you have to complete the connections for the, now you have to complete the connections for the extension headers. So SWDIO is connected. Let us complete this connection. SWDIO is connected. Then we have the, this is done. Yeah, so we have to take it through, we have to connect it to XRES. So let us take it till here. Uh, so switch SW2 is connected here. So let us give some space. Now what you have to do is right click, place through wire, place through wire. Now you take it and complete the connection to XREX. Uh, this is not required, so that connection is done. What else is there? There's a ground and there's a VDD. So there's a ground and a VDD. Okay, so now we need to make the connection. Uh, yeah, now we need to make the connections between the header and the wireless SoC module. So if you look closely, these connections are crossing each other. So GPIO 0 is somewhere, uh, GPIO 0 is somewhere here, and GPIO 3 is somewhere here. It would have been better if GPIO 0 was here, and 1, 2, and 3, the connection would have been easier to make. So it is sometimes during layout we might find that it would have been easy if the connections were crisscrossed. So how can I solve this problem? We can go to the schematic and GPIO 0, GPIO 1, GPIO 2, GPIO 3. You have to make it uh, make P7 2 as GPIO 0 and other way around. So this I will change the label to GPIO 0. This would be GPIO 1. This would be GPIO 2. This would be GPIO 3. So here we are designing the board, so we have the flexibility to change it. So in some cases, the schematic might be fixed, and in that case, you will not have the flexibility to make any change. Now go to the PCB editor, go to tools and update the PCB. Whenever you make any changes in the schematic, you'll have to import that changes in the PCB. Now you complete the connection. So you take the GPIO 3 and complete the connection here. Yeah, so there is something that is blocking this connection. So let me delete that first. Okay, so let me complete this connection first. GPIO 3, now we have the GPIO 2, then we have the GPIO 1. Okay, so then we have GPIO 0 as well. So this would be GPIO 0 is also connected. Yeah, so the GPIO 0 is connected. Now we need to connect the VDD and ground. So we have this ground connection here. So the ground goes here, and there's a VDD connection here coming in. The VDD is going somewhere here, so we can take it from the bottom side. So that completes the VDD connection. Okay, now let us look at the header J3. So in header J3, it would have been good if the header J3 was connected to the GPIOs of the header 3 was connected to 11, 12, 13, and 14. So the connection should have been easy. That is, GPIO 4 is connected to pin number 11. So let us make these changes in the PCB first. So pin number 11 would be GPIO 4. So pin number 11, instead of NOC connection, GPIO 4. So instead of making this as GPIO 4, let us make pin number 11 as GPIO 4. Then 12 was GPIO 5. Let us go back and see it. 11, 12 was GPIO 5 and so on. So if you make that connection, it will be easy to configure it. So 12, 13, 14, you delete it and make it as GPIO 4, 5, 6, and 7. 4, net label, GPIO 5, GPIO 6, and GPIO 7. So you don't need these GPIOs. Delete it and set it as NCs. 40 pin HAL, set it as NCs. Now you have made the changes. Save it. Go to the PCB editor. Now come over here and go to Tools, update PCBs from Schematic, update the PCBs. Now you click clock, closed. Now let us do the wiring. Yeah, so let us do one thing. From here, take a wire. Then from the bottom side, you connect it to GPIO 4. Do the same with the GPIO 5. Now let us finish the GPIO 6. GPIO 6 is done. Now we have GPIO 7. Okay, so that is done. Okay. Now we need to connect the VDDs and grounds together. So VDD is connected, and from here you can complete the connection of so the ground is connected. There is a wire ground connection that is remaining here. So so the ground connection is done. Now the stability clock connection has to be done. Okay, so there are a couple of connections still remaining. Let us look at this. So this has to be connected to LED 2. So that connection is also done. There is still one more ground connection need to be complete. So the connections are more or less done. There is one ground connection that need to be completed here. And let me complete that ground connection. Can use the copper. So most of the connections are more or less done. But I would like to replace this connector with a more generic connector. It's a JST type connector. And I want to replace this connector. So how do I do that? Go to save this, the PCB, and go to the schematic editor. Let us try to change G2 connector first. So double click on G2, change the footprint. So we have different types of connector. Let us select the connector, more generic connector, which is a connector with a pitch of 2.54 mm. And we need to take a 6-pin vertical connector. 6-pin vertical connector. So this is what we want. Click OK. Click OK. So let us come back to the PCB editor and update the PCB. So this is the connector that we have now. Uh, so this completes the change in the connector. Yeah, so this combines a change in the connector. If you want, you can adjust the board size accordingly. Okay, and we also want the connector over here also to be changed to the generic type. So let us do that. Go to the schematic editor. Yeah, for time being, let it be like this. So let us go back here. And if you want to look in the 3D mode, yeah, you can see these are the two different types of connectors which we have made. And you can see the bottom and the top side. Okay, so this is how the board look like. So this is not an optimized board in the sense that there's a significant amount of spaces left empty in the board. So typically when you make a PCB, you need to make it really compact that there should not be a significant amount of empty spaces. But since this is a tutorial on how to design the PCB and to make the PCB design easier, the board size is made much larger than what is required. Okay, so let us close this 3D viewer. So once the layout is done, we need to do a layout check. We call that the design rule check and run the DRC. Yeah, so this says there are issues here which need to be fixed. Yeah, so one of the first issues is in terms of the clearance. So if you give sufficient clearance, it should work. Yeah, so let us look at the footprint U1. This should solve the problem. Yeah, it means that. So let us complete the connection again. Go back. Yeah, so there's no errors now, and there is no errors and no warning. So which means that the uh, layout is more or less proper. Now let us run it again. Let us run if there is any ERC issue. Yeah, so this is a problem. Yeah, so Ideally, it should have taken in the different way, but let us give some space. This should be solved. Yeah, so this looks okay. Uh, let's go to the 3D viewer and see how the board looks like. Yeah, now let us close this. Yeah, the next step, once layout is done and the layout check is done, it is always better to pour a copper on top of it. So how do you do a copper pour? Okay, so the schematic design is more or less done. I made a couple of more changes. The footprints for the all the connectors are being changed, and uh, the DRC is run. The DRC looks okay. There is no more issues in the DRC. There is no errors and no warnings. So more or less the schematic is done. But as a good practice, whenever you are doing a schematic, you also pour copper on the top and the bottom. There are many advantages for pouring copper on the bottom and the top, which is something that is uh, this out of the scope of this tutorial. So I'll show you how to pour copper on the top and bottom of the PCB. So in order to do that, you select the add fill design option, and then select the net, which is the ground. We want the sound to be filled on the top and the bottom. So select both top copper and bottom copper and connect them to the ground and click OK. If you want, you can name the sound. Let me name the sound as Z1, sound 1, and click OK. And you define the sound. So you'll define a rectangle which will sit on top of which will sit on the top and the bottom side of the PCB. So you have drawn a rectangle. So the sound is created. So once the sound is created, we have to fill the sound. So what you do is right click, select the sounds, and you say fill all sounds. So once the sound is filled, you can run a DRC check once again to see if there are any issues. Looks like there is no. Okay, so there is one issue. The sound incomplete. Yeah, so this is about the spot count, which we can fix it in the board setup. Minimum thermal relay spot count reduced to 1. Click OK, and then run the DRC check again. Delete all markers, run DRC. Yeah, so this is done. The DRC is done. And if you want to see how the sound look like, you have to go and look at the 3D viewer mode. So in 3D viewer, you can see that copper is filled over here. So copper is filled on the top as well as on the, if you look at the bottom side also, the copper is filled. And this copper is connected to the ground net. So if you can look at here, this is a ground connect. This is a ground pin, and the ground pin is connected to this copper. So you have now copper on the top and the bottom, and it is connected to the ground. So that completes your layout. The next step is to generate the Gerber files and bill of material so that it can be used to fabricate the PCB. So the layout is completed more or less. The next step is to generate the Gerber. So even before generating the Gerber, let us name this board. So go to the cell screen and then go to the text option and say that uh, this is a um, this is the PSOC 6.3 BLE board version 1, and you can place this on the board. And once it is placed, we can do one more design rule check to see everything is fine. Run the DRC, and it looks like everything is fine. There is no errors and no warnings. So you save this project. You save the layout. The schematic is fixed. Schematic is checked. Then the layout is completed. The layout DRC is checked. Design rule checking is done. There is no errors in the schematic. There is no errors in the layout. We have also poured the copper on the top and the bottom and connected this copper port to the ground. We have labeled the board. The next step is to generate the fabrication files, also known as the Gerber files. So how do you do that? There's a straightaway way to do it. The option is called is done using a plugin. So KiCad supports adding plugins. So there is an option, there is a plugin that is available called Gerber to order. So when you install the KiCad, this plugin will not be available. So if you want to install this plugin, you can go to the uh, home of the KiCad, and there is an option here for plugin and content manager. So click on that. And here you can search for Gerber and you can install this. Currently, it is already installed. If it is not installed, you can install that plugin. Once a plugin is installed, it will be visible in the layout editor or the PCB editor of KiCad. Yeah, so there is an option here. Go to Tools, External Plugins, Gerber to Order, and you click on Export. So once it is done, it will generate the Gerber files uh, in the project directory. And the Gerber files for most fabricators, you can use the default.zip. So this is a zip file. Default.zip will contain the necessary Gerber files, which can be used by the manufacturer to fabricate this PCB. So to figure out where this is, to figure out the location of this zip file, what you can do is you can go to the KiCad project folder. So go to the KiCad. Yeah, go to the KiCad home and go to the folder location. And in the project folder location, there is a folder named Gerber to order. If you go inside the Gerber to order, you will see the default.zip file. Yeah, so uh, this is a zip file that you need to send to the PCB fabricator so that the, the PCB fabricator can fabricate your PCB. Before sending, it is also a good practice to view this Gerber file. And there are different softwares available to view the Gerber files. There is also an online tool called Altium Viewer, which can be used for viewing this Gerber file. So you can upload the zip file. So go to Upload and go to the project directory and select the default.zip file, open. It will take some time. The zip file gets unzipped and the Gerber files will be available to view. Yeah, so you have all the layers which are available here, and then you can verify that the Gerber is correct. In most cases, it will be correct, and you can send the zip file directly to the PCB fabricator. So the next step is you can send the Gerber file to the PCB fabricator to fabricate the PCB. The next step is to export. So the final step is to generate the bill of the materials. So there are multiple ways you can do that. You can come to the schematic and there is a tools option wherein you can generate the bill of the materials. Here you uh, specify the file name and then say OK. So it will generate the bill of the material in the project folder. So you can go to the project folder. Yeah, so let us go back. It is not generated. So go to the tools, generate bill of materials, and click on export. So now the bill of the materials is generated in the project folder. So you can you can click OK, and then come to the project folder, go to the project folder, and you should be able to see the BOM file, which is the CSV file. You can open and see how the file look like. There is another way to generate the BOM in a different file format. So go to the layout part and go to the external plugin, generate interactive HTML BOM. So this is a plugin which need to be installed just like the way we install the Gerber to order. Click on the generative interactive plugin. Now click on generate BOM. So this will generate a HTML file in the same project directory. Now the advantage is that it has a BOM, bill of materials listed. At the same time, it has an interactive way. So let us click on a component and you will see what is a component value, reference, designator, how many quantities of the components you want, and so on. Yeah, so that completes a PCB design tutorial. You have learned how to create a KiCad project, how to create a schematic, how to do an error checking of the schematic, how to create a layout, how to do a design rule check of the layout, how to pour copper at the bottom and the top of a PCB and connect it to a ground net, how to generate Gerber, and how to generate the bill of the material. Thank you.